So in a way, the topic needs no introduction. I just want to talk about active materials, so living materials out of equilibrium. I know there have been quite some talks on this already. Over this, Irene Giardina was here, and I just wanted to show you a couple of the classic movies to start with. So this sort of stuff was what started it all. We can play this one too. So collective movement of things like sheep here, with sheepdogs, or birds, in particular, the very celebrated starlings of Rome. I don't know if they're aware of their fame, actually. So as you can see, these flock together without a leader. And in fact, we figured out over the years that there's more than a bit in common between these two systems, but that's not what I'm mostly going to be talking about here. So instead, I would like to look at active matter at different length scales in different circumstances. In particular, if I go down a couple of length scales and become more biological, I can look at active materials at a much smaller scale, such as these here. This is bacteria doing E. coli doing a run and tumble. So if you don't know what a run and tumble is, it's they go straight in one direction because of their combined flagella moving them. Then they will stop, although not like this movie. Play it again. Reorient themselves, tumble, realign the flagella and move in a different direction. So this has been mapped to what we call active Brownian process later on, some years ago, but the idea of this, that this makes you a good search pattern for looking for food if you're an E. coli. So even more biological, you can look at active materials and you can look at cell sheets. So these are everybody's pet lab cell, which is called MDCK, muddy Darwin canine kidney cells. So that's cells from the covering of kidney of dogs. No, don't ask me how they came up to that particular cell line. I don't want to know. But we have looked at them in quite some detail over the last 10 years or so. What you can see is that they make collective motion, which is sort of like swirly, which resembles glassy materials. Yes? This thing is already on. I'll try to talk louder. Yeah. Sorry. Is this any better? Yeah. Is this any better? Okay, I'll try what I can do. My apologies. Essentially, let me go back to the cell sheets. Yes? Is this any better? Can you hear me now? So as you can see, the collective motion of these cells, it is very complex, and there are many different interpretations of these over the years. But as you can see already, this thing has a combination of things corresponding volume exclusion, crawling, things moving past each other, things resembling dynamic heterogeneities, but also wave propagation. And you can see here waves in a strain pattern. So this has been interpreted, for example, something I won't have time to talk much about, active pneumatics made out of cells pulling on each other, but also approaches within the glassy framework, which we will talk about. Then if you start talking to biologists, they will tell you, well, in fact, guys, you're having fun with these MDCK cells, but this is not what we are interested in. What we're interested in is true biology, like, for example, this here. So this is what's called gastrulation. So if you don't know gastrulation, it happens to every animal. It happens very early in development, where the developing embryo turns inside out, and it becomes from a sphere to a tube in the process. This is also the reason why we have an entry and an exit. So this is this old, this biologically conserved, so it's important to understand. You can see it here on top. Let me play this one again. For a Drosophila, so a fruit fly, and at the bottom, this is the same thing for a chick embryo. And this is topologically the same process. You'll see the folding happening here in a moment. I hope to say a little bit about this later. Now, after these very biological examples, which of course are very hard to understand, because many different things are going on. People said, let us go to the lab and maybe we can in fact make active materials in the lab which are better behaved and which we can understand. So one very celebrated system is this one here. That's originally a group of Zvonimir Djoric, and this is microtubules with kinesin motor clusters in there. And so what they do is these kinesin motor clusters make these filaments pull over each other. So they make this living liquid crystal, pneumatic liquid crystal, which has become known as an active liquid crystal, here with self-propelled active defects throughout the material. And if you plate these things on a sphere, you can make these really striking oscillating defect patterns for these materials. So this is one way of taking parts of a living system and making artificial biomimetic material out of this. I should say you can also do this in different ways. You can make artificial collective motion using really purely mechanical pieces. For example, these little funny toy bots, so hex bots. So they vibrate and then they start moving, yes. So for example here, Paul Bacconnier with Olivier Dauchot recently made very good use of these with a lattice to couple this to an active solid where this thing is collectively oscillating and actuating. And I will come back to this motion later on. Now, much more simply, in fact, this is part of an art project I was involved in. This is fun. You can, in fact, just vibrate a plate and have some chalks with rubber band on one side and nothing on the other side. As soon as there's any asymmetry in this thing will start moving. For example, like if you have your phone on the surface, when it vibrates, it will tend to move. That's the same effect for why these guys move. So you can make this quite easily. You can also, and let me play that movie again, make this work using formal robots. So these are called kilobots. They're small programmable robots. In this particular case, they've been programmed to sort themselves out to make a star, not completely freely, but something in between programmed and self-assembled. Now, that is very nice and very beautiful as a system, but the main workhorse of active matter is actually not these guys. The main work of active matter is something which is just much smaller, much more controllable, and which fits into your lab, and that's colloids. Yeah. So if you're not familiar with colloids are roughly between 1 and 10 microns, or sometimes smaller, usually spherical, like glass beads, PMMA, and you can fluorescently label them, and they're also everywhere, like in food, in mayonnaise, or in sunscreen, okay? So there have been many ways of making these active, and I'm just giving you an overview of some of them. So the first and still most commonly used ones are Janus particles. The Janus particles are typically something with platinum on one side and nothing on the other side, and they catalyze a fuel, for example, hydrogen peroxide, then they start moving. And so this was done already some time ago now, and so they use the surrounding as a fuel, and then depending on the concentration, you can get them to move and self-propel. Like here, if you have nothing, there's just random organ, otherwise they indeed start moving. More recently, people have started making more controlled ones. I don't know why these don't autoplay, I asked them. So these are light-activated colloids, and the good thing is you can turn this on and off, and this has been since used also to make proper patterns. So you can turn them on and they start moving. You turn off the light, they will stop moving. And just turn off the light in a moment. There you go, falls apart. Light on. Starts moving. Now, whether this is MIPS or not has been a long and complicated discussion. I don't want to take a point on that situation. Now, you can also make other ones. For example, a very celebrated system is something called Quinker rollers. So Quinker rollers are due to an exotic effect called Quinker rotation, where you put an insulating sphere into a conducting liquid and you put an applied electric field. Then, with the right combination of dielectric constants, this thing starts to rotate. So you develop a net torque, and the whole thing, if you put it on the surface, is going to start moving on its own. And it moves fast, much faster than, for example, those self-propelled colloids. So a low density, so come on, play. So you can see, for example, here, these ones do flock together, much like the birds or like the fish. And in fact, you can really look at solid-liquid transitions, and this has been mapped, or more or less mapped, to the WICHEC model. Now, in summary, and this is just my intro, you can make many types of active particles, and they're very useful, and this has been quite developed over the last 10 or 15 years or so. So after just introducing the topic, I would like to start what is really supposed to be a tutorial by asking what is the simplest equations I can write down for this, be useful and get something out of. And I think, especially after what we saw this morning, there's not going to be any surprises there. We're going to write down active Brownian motion. So what's the simplest useful model of this motion? So I wanted to, in about 40 seconds, review the Langevin equation. Now I know this audience doesn't need it, but I wanted to set the basis and define my notation. So if I write down Newton's equations for, say, an active colloid or something like this, moving through a fluid, or even a cell moving over a substrate, I should write m times a is equal to f, yeah? And the forces I encounter are dissipation forces with the surrounding fluid or substrate minus zeta dr by dt. I could encounter external forces, where we put self-propulsion or gravity or something like this. I could have forces with other particles, which I'll write down as pair forces, and I'm going to have fluctuating forces due to thermal noise. Now, the overdamped Langevin equation says for things which are about a micron size, I can do a Stokes flow approximation, say this thing here is negligible to this one because the mass goes like r cubed, whereas the friction only goes like r, yeah? And so this dominates. I rearrange my equation. I write down the overdamped Langevin equation. dr by dt is mu times external forces, pair forces, and fluctuations. And then if I'm in thermal equilibrium, and fluctuation dissipation is valid, I can write this noise as correlation as 2d kbt over zeta delta ij delta t minus d prime. So uncorrelated in time, uncorrelated between particles, when the prefactor strictly linked to the temperature of this particular system. Then I can compute the diffusion coefficient for this thing as 2 times d times t, where d is given by kt over zeta, and zeta I can write down in Stokes law as 6 by eta r. And so, okay, this is very much intro to soft matter everything, yes? But I wanted to remind you, for something like an active colloid, I will diffuse a diameter of its own diameter in approximately 1 second, which is why this is nice to observe on a microscope. So, having reminded you of all of this, let's make this stuff active. So, for active Brownian particles, I'm going to assume that my colloids or my cells or my slugs or my whatever they are, yes? Was there a question? No, okay. Move over a substrate, and they move over a substrate such that there's friction with it, and self-propulsion, I'm going to write this as an overdamped Langevin equation in the same form I just had. So friction coefficient here, I'm going to write these external forces as F active in some sort of n direction. So I'll write this as an active force generated through, say, crawling over the substrate in some direction n, which makes an angle theta, angle phi in this case, with my axis. And I keep pair forces, I keep noise. And then the important bit is I'm going to write my active force. I need a dynamical equation for my active force. So active Brownian particles is the simplest thing you can think of, which breaks equilibrium, which says phi dot is itself diffusing so there should be a 2 over tau r delta t minus t prime. So there is a rotational diffusion constant here of the angle changing in time. So this is, in a way, the simplest way of making things active. And what I wanted to do briefly on the board, just essentially as a small tutorial, is derive the behavior of a single active particle. Any questions right now? How is the speed? Too slow, too fast? Okay. Okay, yeah. So we'll do one active Brownian particle, and I'm going to put this up for now. Do we have light on this thing? So let me write down the equations of motion for active Brownian particles again. So I'm going to say I have several of these. I'm going to write them as Ri dot equal V0 Ni plus mu times sum over j Fij plus eta I. And I'm going to work explicitly in 2 dimensions, where my particle I has a vector Ni, which makes an angle theta I with the x-axis. So I'm going to write this as theta I dot is equal to sum over, so rotational diffusion constant, sum over j pair torques plus eta I r. So let me explain briefly. So the first equation is the same one which you have seen already. In the second equation, I've now essentially taken the overdamped limit in rotation space as well. And so this would be, this here is our pair torques, yeah? And I'm going to give you an example of these later on, which corresponds to alignment. But what I'm going to do for a single active Brownian particle to actually solve this thing analytically, I'll make a very simple approximation. There will not be any pair torques and take a single particle. There won't be any pair forces. And I'm also going to remind you of the noises. So the eta I t eta j of t prime is going to be 2 dt delta ij delta t minus d prime. So translational diffusion constant, and for the rotation ones, eta jr of t prime is equal to 2 dr delta ij delta t prime t minus t prime. Okay, so far so good. And to solve this thing, I need to solve both of these equations. And so the good thing is, as you can see, once I've neglected my pair torques, this equation here is idiotically simple. I can solve it as is. This just says theta dot, so one particle here. It just says theta dot is eta r. I can solve this formally as theta of t as an integral 0 to t eta r t prime dt prime. And from this we can compute all of our moments easily. So you can see already that on average theta of t, this is the ensemble average. I can take this out here. I can average this. I should say, in addition to these, I should have mentioned, it sometimes seems obvious, that both eta of t, the spatial noise on average is 0, and the rotation noise as well. So assume they're both Gaussian distributed, although this can be done slightly more generally for the orientational part. So I do this. I'll do it once specifically. Eta r average here, t prime dt prime. As you can see, this is 0, but one which is not 0 is theta square of t.
because it will take too much time, so I can write it out as a double integral. I can compute it. I get a computation. I will end up with eventually 2 dr times t, or 2 over tau r times t. So this is the same calculation as you would do for diffusion constant. So you compute this sort of thing, and you compute it. Yeah. Do you see where this comes from, or should I do it? Okay. Seems like people are okay with it. Yeah. So thing is, I solved this equation now, that's fine, but I would like to solve active Brownian motion in general. So what I need to do now is I need to in fact know not the properties of theta, I need to know the properties of n. Yeah. So I need to compute n, which is cos theta sine theta. So the way to do this, unfortunately, there is no shortcut here. So since I know the first moment, the second moment, I can compute this using an expansion of the cosine and the sine into a series of moments. Okay, so it's long and annoying. And so in particular, I need all of the moments. So for example, theta to power 2n, I can compute it as constant times theta to the power 2 square to the power n. And so the even ones I can compute as a function of the square, and the odd ones are all 0. So from this I can compute all of these, and then I stick them back in, and I will eventually be able to compute that on average n of t, so the active direction is 0. That makes sense because on average I'm not pointing in any specific direction, and that the second moment, I'm going to write it as v0 n of t dot v0 n of t prime is equal to 4 times, I'm going to write it as v0 square over 2, 1 over tau r e to the power t minus t prime mod over tau r. So let's step back here and try to understand what we've just derived, yeah, or what I've given you an overview of. So I've computed the correlation functions of the active driving, and this one is interesting because this one is time correlated. So this has memory and correlation. And what this means is, let's draw a couple of trajectories. We do it properly, but let's understand what's going on here. So if I had a single colloid, yeah, so if I was going to draw its trajectory, it would look something like this. Yeah. So this is diffusive. And there is no persistence internally to this trajectory, so I can point one direction one moment and the other direction another moment. Now this guy here, as you can see, this means that there is, so if I'm going to draw the trajectory, it will look something like this instead. And what's going on here is that the active driving makes this thing persistent. So for example, if my particle is pointing here at this moment, and here at this moment, t prime, as you can see, if t and t prime are sufficiently close, they are correlated with each other. So that means I'm going to only change direction here over a certain time scale tau r. So essentially what's happening is that the existence of this active persistence has introduced a persistence length
V0 times tau r inside the system. So this thing is persistent now, and this is known as a persistent random walk. So the idea here is that you can distinguish them. They have different statistical properties very clearly because of this memory kernel. So I wanted to also say something else, which is that this thing here has a formal limit, a formal thermal limit, and I've written it here specifically like this, and make me certain I don't mess up my factors of 2 here. So this thing here, 1 over tau r e to minus t prime over tau r, this goes to my delta function as tau r goes to 0. Yeah, so this is a thermal limit. This thing disappears as a delta function. And let me see, did I make a mistake here? Yeah, I did make a mistake. And the mistake was there is another tau r here, which cancels with this one. And what's happening is here, this prefactor here we're going to call this an effective temperature. And I run out of time here, yeah. So what I want to say is I'm going to write, this is going to become part of the diffusion coefficient, and I'll clarify this in a moment. This is going to be my active diffusion coefficient, mapping to an effective active temperature. Just bear with me for a second, we'll derive the mean square displacement, it'll become clearer, yeah? So in fact, let me do just this, erase this piece. So to be more clear about what's going on, yeah? So what I should do here is I should compute the mean square displacement. So the mean square displacement is going to be the r of t minus r of 0 square average. And to compute this, as you can see, okay, I'm going to have to really integrate my trajectory, and since I'm doing it in 2 dimensions, I should do a mod here. So this is again a long complex calculation, and I'm using the properties I've just derived here. And after a long calculation, this is going to be 4 dt t plus 2 v0 square tau r times t minus tau r 1 minus e to the power minus t over tau r. So let me explain what's going on here. So if I'm going to plot this function, so log t and the log MSD here, it will look as follows. More or less like this. So what we have here, and let me annotate this, we have a change between a slope 2 and a slope 1 at exactly tau r. And in fact, the two limits of this function, you can compute them. So if t is much smaller than tau r, and I'm going to neglect, so there's a thermal component, this is the plane thermal. So I'm going to neglect this for a bit to make the point clearer. Then I'm going to get the MSD, which is V0 squared T squared. So you see this, you see the scalings 2 here, okay? And that makes sense. What is V0 squared T squared? This is going in a straight line. So this is ballistic motion in a straight line. Now, the long time limit, however, so which means in t much bigger than tau r, I'm going to find the MSD as 4 times dt plus dA times t, where dA is nothing what we had before, V0 squared tau r over 2. So you can see what happens is at a long time, this thing behaves like it's diffusing like an effective passive particle, but with a higher diffusion coefficient, which has an active component, in fact. And since we know that this should be 4 dt, yeah, in general, I write my effective diffusion coefficient as dt plus V0 squared tau r over 2. And in fact, since I'm also going, because of fluctuation dissipation, which would say for a thermal coefficient, I would write this as kBt over zeta. I'm also going to write this one as kBt effective over zeta. So I've defined now, like I threatened earlier, an effective active temperature for this system. So because at long times this behaves like a normal diffusion, I can define from the long-term limit an active diffusion coefficient V0 squared tau over 2, from which I can define an effective active temperature as well. Okay, so this is one active Brownian particle in a nutshell. Questions? Yeah. 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 Yes, so yes, I could. And like, for example, you can get the same motion actually much more simply by taking a particle with mass. So a system with mass also has, if you want a memory kernel like this, and it's going to formally do the same thing but for different reasons, yes? Yeah. Yeah. From a single one, from this calculation, I agree, it's not obvious, it's not entirely obvious to see. However, even for a system with mass, you would not get a second piece, so diffusion coefficient, fluctuation, dissipation would still be valid. You would retain this, and you would not get the extra piece. So that's one way of seeing. Even though I agree, at short times, you get a piece of slope 2 as well, but for different reasons, yeah. Yeah. Yes, agreed, yes. But you can put numbers in there and actually do this in my course. This is something like 10 to the power minus 7 seconds for a colloid, where the mass matters, so it's not a region, which is observable usually. So numbers matter at that point. You don't see it for something that size, yeah? Anything else? Then let me turn this thing on again. Okay, so this is a visual summary of what I just derived for you. So different statistical behaviors. So what I'd like to do now is explain to you a little bit of how to simulate these. And in fact, you should be able to download, and it's been sent around, a Python file called activebrownian.py to run, and I'll demonstrate it for you here on the screen as well. So keep in mind, this is, again, just a demonstration. In fact, I teach this as is in my course in Leiden. So the idea is, how do I simulate something like active Brownian particles? Okay, so we've been here before. Here's my equation of motion for the active Brownian: self-propulsion, pair forces, thermal noise, which is correlated with standard thermal diffusion, and orientational equation of motion, which is just random noise. Okay, so as you can see, this is a stochastic ODE. So if I want to simulate this, and I think this audience is probably the one where this is least necessary to explain, I need to also integrate this properly using an integrator compatible with stochastic processes. In particular, we have two stochastic processes in here. So we have the thermal fluctuations and we have the orientational fluctuations. So we're going to assume that both of these are Gaussian. And so here I've given you here for the persistent random walk of the active Brownian particle, I've given you a distribution here with mean 0 and width square root of 2dr. So if I want to simulate these, I need to take this into account. But I also have, at the same time, before I get there, I have in fact also forces in here which are not stochastic, which are deterministic. In particular, I have the pair forces in here. And so just for realism, I want to talk a little bit about what I choose here for pair forces for this to be useful, for example, for cells or active colloids. So what's the simplest thing that's useful in here? So what you want is something which are forces which are repulsive if particles try to overlap. Okay, so they're not all sticking on top of each other. You want them to be short range, so 0 if you go for long distances. And you want them to be, for simplicity, pairwise additive. I will relax this once we talk about cells later on here. So there's many options, and so for something hard like colloids, I usually want to use something which has a very steep potential, like a Lennard-Jones or weak Chandler-Anderson potential. Now, that's difficult to simulate out of the box very easily. So here I will use something simpler, which actually turns out to be good for cells as well. And that's one-sided harmonic springs. So this is what it says on the tin can. I have particles which can squeeze into each other. And if they squeeze into each other, there's a potential between the two, which is a K2 times what turns out to be the overlap between the particles square. So Ri minus Rj mod minus the sum of the radii square. So that potential is harmonic if I'm overlapping, and it's 0 otherwise. I can take the gradients of these, I can compute the forces formally, and what I will get is a linear repulsive force minus k times overlap in the direction of the overlap and 0 otherwise. So this is, to the best of my knowledge, the simplest useful potential for doing active materials. And so this is what we're going to use for this little exercise. And so the one thing I need to do now is combine what I said about stochastic ODEs and potentials, and write down an algorithm for this. So I wanted to remind you or introduce to you it was called the Euler-Maruyama algorithm. So that's the simplest way of solving stochastic ODEs. And so I think this is, for most people here, probably revision, but the idea is that if I have a single stochastic ODE, or multiple x, could be anything here, I have dx by dt is a deterministic part plus a stochastic part, which I'm going to write as b times some sort of noise, which here is perfectly Gaussian normally distributed, n01, okay? Then if you translate this into the probability theory language, which I think people here in this community also use, I'm going to write this as dx of t is being a function times dt plus b function times dw of t, where dwt is a Wiener process, or also known as a random walk in the more physicsy community. So the idea of the dwt of t, and I've drawn one here for you as a function of time, so it's the same sort of random walk we derived for the angle of the single active Brownian particle, is that it's 0 on average
and its mean square average is time dependent. So this is the same calculation as when one does a diffusion coefficient calculation. The dw of t square, if I integrate it over a time step, as written here, a finite time step of my probability of my algorithm I'm developing, that it's equal to dt, not dt square, for the same reason as the mean square displacement goes like t and not like t square. So this has consequences because the WT average is 0, but its square average isn't 0. And so for my algorithm to work properly, for me to integrate this thing correctly, I need to scale my noise in the stochastic part so that it's consistent with the Wiener process. So what that boils down to is, while for the deterministic part, I can write down an algorithm which is a classic Euler, so xtn plus 1 is x of tn plus a times dt. The stochastic part is b times the noise, but the square root of dt to stay consistent with the statistics of the Wiener process. So I know it seems like a little thing, but I've over the years keep getting papers to referee which do this wrong, so I just wanted to make certain to mention it again, yeah? So once you're done with this, and the potential in all of this, we're essentially done. So we get the actual algorithm for active Brownian particles. So we have 3 equations per particle for x, for y, for the angle. And they have a deterministic part and a stochastic part. So 3 and total equations. Algorithm here, x, y, and angle. Deterministic piece, which is the active force and the pair forces, and stochastic piece with the square root of dt in here for the x, for the y, and for the angle. Okay. So let me actually pull up the code. Yeah. So let me make this bigger. Okay, sorry. So I won't go through the code, but it implements the algorithm. So the point here is this is a small Python code which is interactive, and it takes various arguments, so like packing fractions, mean speed, temperature, rotational diffusion, constant, system size, polydispersity of my particles. So it implements everything I just said. Just wanted to point it out. My main computation is in here. This is the potential calculation. And here are the stochastic pieces. And I'm just going to carry it out once for you. So what you see here is in real time. So I would recommend you try this out. So what's happening here is, and I hope this worked right. This is the one machine. The scaling isn't working on great. So this is supposed to be. God damn it! Sorry. Yeah, here it's better. This is what it's supposed to be. So you can see the then. So these are active particles. The red is the velocity. The yellow is the self-propulsion direction. And so what they're doing here together is this is about 50% density, and this makes sort of a situation which is close to MIPS, but not exactly. You see strong density fluctuations already. You can also change this thing using my arguments. For example, if I want to make, say, an active glass out of this, yeah, I can make this. Wait, let me make this first a bit bigger. I can make this a packing fraction, which is 1. And I'm going to reduce the driving to, say, 0.05. And yeah, this is the one system, unfortunately. Normally, this should work on any screen, but the scaling of the radii is such that it should be exactly consistent.
Okay, I wish one of you would please run this. This doesn't look quite as well as usual, but what you can see here is that I've generated now a packing of all of the particles being stuck there. This hasn't happened before. It's always worked so far, yeah? Yeah? Yeah. Yeah. Yes, exactly. So I have one more slide to show you. I really encourage you try this out. I wanted to have one more slide, and that's then starting to move into your part. Is that this thing can do one more different situation, and the situation it can do is this code can also add polar alignment to the system. So I had mentioned pair talks earlier on, but I hadn't said anything about them. So in particular, pair talks between the angles of different particles can make the system flock. And in particular, the one I implemented for you is minus j sine theta j minus theta I. So that's like an XY model. This will align different spins of my particles with each other, and since this thing is moving, this makes a flock. So this is a close relative to the Witschek model, which I think you'll mention in a moment, and this has a transition from a ordered phase at low noise to a disordered phase at high noise, or alternatively ordered at large j. So right now I was running this with no j, and this is the last one I'm going to run before handing over. I'm going to run this with strong alignment, and it's going to flock. Let me keep it this size. Assume the circles are bigger, yeah? But you can see that this thing now is going to make a nice flock. So please play with this. It can make all of the different phases. And on any screen except this one so far, the arrows should actually rescale themselves properly. So with that, I'm going to hand over, for the first time at least.
There are no questions?
Yeah. Yeah. Okay, yeah.
Okay, so first I want to thank Silke for giving this introduction, also because I guess that most of the people here don't work on active matter or have a very generic view on active matter. So before giving the pause, for which I think I have maybe 20 minutes, something like this. 10, let's say 15, come on. What I wanted to tell is about collective behavior in active matter and why I think this is interesting, why this is relevant, but also to tell you what are the main established things before we move on to the most recent part. And I will ask you some questions that you may find very dumb, but I would like to understand why they're not dumb. And the first question is why this doesn't work. The second question is, we've seen aligning particles. So can aligning particles actually lead to polar order? You had a lot of spoilers of that. Who says yes? I'm glad that there are some people saying yes, because the answer is actually yes. This is typically the flocking that Silke has been speaking about, and this is what happens when you have particles that align, like in the Witschek model that we're going to see about. When you put a bunch of particles together with interactions that can be repulsive or not, and you say that particles can align, you can create a model where you have something flocking, like what we see in the sky of Rome, and this has been said. So this was the first model of flocking that came out, and we are in the 1995 when Witschek introduced this model, saying, okay, we have a collection of particles, they update their position just with a Euler dynamics with a velocity, which is given by orientation, which is described by an angle. Theta is the theta you saw before, and theta can change, is updated with an alignment rule that makes it align with the average angle of the particles within a radius r from the single particle I, and a delta theta, which is a noise, which is described by this amplitude eta. Once you have this, you say that you have two control parameters in your system. You have density rho, the number of particles you have in your volume, and the noise eta. And then you can look at the order parameter. When you want to describe a flocking system, the order parameter is the collective self-propulsion VA, which is nothing but the order parameter you would have in a ferromagnetic system, counting, summing, doing the vectorial sum of all the spins, and then normalizing it to the number of particles and the speed v naught. And when you do this, you see that in this case you have that at low noise or high density, you have that interaction matter and noise, and when noise is low enough, which is like saying temperature is low enough, you can align. But now comes the second question. Why is this so surprising? Why am I asking you this question? If anybody has a hint? Very good point. So exactly this was, the surprise of this was that actually we see that this is a system with continuous symmetry, where the flux, the spins are able to rotate in a continuous way, and we knew since the 60s that Mermin-Wagner prevents the appearance of long-range order in 2D when you have a continuous symmetry. But this is the fact that when now we are speaking about active matter, so being active means that you can do a lot of collective behavior, you can have a lot of phenomenology, but you have to forget about free energy, you have to forget about Boltzmann distribution, you are out of equilibrium intrinsically. And so this was what motivated also the community. And also when you say, okay, we see the transition from disorder to polar, things can get also more complicated than this, because actually people for a lot of time have thought that there was a disorder gas followed by a polar liquid, but then what you have is that in between these two phases, if your system is large enough, so what does it mean large enough? Larger than these bands, you can develop a microphase separation where the system spontaneously segregates in different bands that are flocking together, where you have here a dense part of the system followed by a dilute part. So this is what reminded a bit of a first order like scenario. And in very recently, a question which is arising, and I don't want to go into this question, I want to tell you that there are this paper, this is an open question, is does true long range order even exist? Because especially this group of people has started in the last year to work on toner 2 equation, which is the equation that describes at the field theoretical level the evolution of flocking, and trying to perturb it in many ways, introducing a spatial anisotropy or introducing a large small obstacle that perturbs the homogeneous state of polar flocking. And so these people have some arguments that this question is actually an open question at this stage. Yes. Yeah. Yes. I don't know how you would, if mapping this to an energy works when you don't have detail balance, because all the mapping with an equilibrium is somehow blurred in this case. You can surely do what you say, like you take your probability distribution and you go back and you define an effective energy in this way. But I don't think this the same structure of the derivation of Mermin-Wagner holds. Okay. No, what I'm saying is that these papers are saying that if for instance here, what they are saying is that if you break spatial anisotropy to a given, like moving from a big sec model where the angle can rotate everywhere, and you introduce a small anisotropy when you have like a clock model, also in the limit of Q going to infinity, you will be in the thermodynamic limit you reach before you fall earlier in the Ising class as compared to the Vixec class, where you basically have macrophase separation rather than microphase separation, which means that you don't have a short scale correlation. You always end up in a long scale correlation. Okay. Okay. So the second question I wanted to ask is, now that we understood the behavior of active particles, is a self-propelled particle attracted or repelled by the wall? Who says repelled? If an active particle touches the wall, does it get attracted? Does it stick or does it go away? Okay, so nobody was distracted by the WhatsApp messages. This is good, and this is indeed the reason of motility-induced phase separation. This again is the movie that Silke has shown before. You have particles that are activated by light, and in the moment the light shines, you create these clusters where the particles merge. And this is also what you see in simulations, like in the one on the right, where you have the formation of the coarsening that forms these clusters of self-propelled particles. And the mechanism of this is something that you don't have at equilibrium, because when you imagine that you have three particles colliding, the particles touch, but if their velocities are pointing in the same directions, these particles need a time to reorientate. Whereas for a Brownian particle, this time is zero. It's zero because you're Brownian, and therefore you need a time to escape this configuration and then to melt the cluster. Whereas when you're Brownian, this would never happen, and so this induced to have positive feedback and gives you a velocity. It gives you a velocity field which is density dependent, meaning that you have a correlation between velocity and density, which is totally forbidden at equilibrium because of equipartition theorem. And on top of that, you can also derive a criterion for the stability of the homogeneous state, which is when the derivative of this velocity in function of the velocity in function of the density is smaller than this quantity. Then you have the homogeneous state is unstable, and that the density fluctuation can grow instead of shrinking, and you create MIPS. And this has been actually mapped to equilibrium, because when you do the simulation and you compute in function of the Peclet number, which is proportional to the self-propulsion and of the packing fraction, you see that the system creates a region where you pass from at low self-propulsion to a unimodal distribution of the density throughout the system to a distribution that splits into two peaks, which is something that reminds a lot of the spinodal instability and in liquids. So now, before stopping for the pause, I wanted to ask you, since here we want to deal with dense systems, and this school is a school on complex Glassy systems. We saw that putting some activity is increasing to some extent, as increases the diffusion coefficient, for instance, a long times, as Silke has shown before for a single particle. And the question is being active, does it help to fluidize or to compact a dense system? Who says fluidize? Who says compact? Oh, there is a huge majority. Okay. We'll see. So, indeed, what I wanted to point out is that being in motility-induced phase separation is not being glassy. So this graph has actually it's actually been plotted in a reference by Silke and co-workers, where you see that changing the self-propulsion and changing the packing fraction, you can identify two regions. One where you have phase separation inside the liquid, and one where you have glassiness, which is defined by the fact that the diffusion coefficient at long times goes to zero. But sure. And for precise definition of the axis, you can look at the paper. And so what has people done is that started studying dense active matter and to see how activity was affecting the glassy transition. And then to do this, you do exactly what Silke has shown before. You simulate the dynamics of particles with a position Ri, which are subject to interaction forces V, and with a persistent noise F, which is only defined by, as you may have understood, an exponential correlation described by a persistence time tau p or tau r, as before, and something that one can call an effective temperature Tf. Forgive my factor 2, my dimensionality, let's say that it's all good, and which has a proper equilibrium limit when the persistence time goes to 0. So what do we expect in this case? You know that if you are monodisperse systems, you expect crystallization and the melting transition. But if you are polydisperse, you can go into the glass transition. And I want to pinpoint that there is no explicit alignment here. We are looking at what is called scalar active matter. And then one can say, okay, let's see what happens. And these results has been reviewed in this very nice paper. Let's see what happens when you have when you look at the self-diffusion coefficient, that then can help us identify a critical value of the glass transition when one fits the behavior of the diffusion coefficient with respect to the density with a Vogel-Fulcher law, and therefore can extrapolate a behavior of the critical value of the density phi c as a function of tau p and the effective temperature Tf. And this is what you can see here. That basically, if the effective temperature is low, the red curve is Brownian dynamics. It's what happens in a thermal system. Therefore, you see that at this temperature, of course, the glass transition at a low temperature comes at an earlier density than the glass transition at a high temperature. But if you look, for instance, at the black curve, which is at tau p equal to 10 in their units, at small times the glass transition is shifted to the higher temperatures, whereas at small temperature the glass transition is shifted to higher densities, whereas at higher temperature the glass transition shifts to lower densities. So the answer to the previous question is both. And this you can see it because when your temperature is very small, some activity actually helps moving because you are almost quenched, you're almost frozen. Whereas when the temperature is very high, this creates the particles are actually hampering each other, and this actually helps the system getting clogged. And this can also be understood looking at the fact that the activity actually resembles an effective attractions when you look at the pair distribution function of these systems, and you see that with the activity you are both shifting the peak and increasing a lot the peak, moving from the red curve, which is the one for a thermal system, to the black one, which is the one for a active system. So now another question is polar order without aligning interactions possible? Yes? How many yes? How many no? Okay. And the answer, if we frame the question in this way, the answer is actually no. Because when you speak about polar order in active matter, we speak about what Silke was showing before, so the ordering of the self-propulsion of the particles. But then there was another phenomenon that was observed in active matter, which has no equilibrium counterpart, and this is the development of longitudinal velocity correlations, where you see here, from that expression, you take your system, you compute the velocity correlation of the velocities of the particle Ri dot, Rj dot, and you go in Fourier space, you take the longitudinal part, and you see that this actually this correlation for different values of the effective temperature and of the density develops this shape, which is not a flat shape, which would mean no velocity correlation, which is what you would have at equilibrium. So what is happening here? Well, indeed, we have no aligning term between the self-propulsion. Therefore, if you look at a snapshot of a phase-separated system, in this case, this is MIPS. This is not a glass, but this effect comes before the glassy phase. You see that each particle in this simulation as a color which correspond to the orientation of their self-propulsion. And you don't see order. You don't see an island of green particles. But if you look at their velocities, their r dot I, you will see that velocities actually align, and those are given by these arrows. And why this? If you want to have a physical interpretation of this, is that when you have a bunch of active particles, these are clogged together. In the cluster, they push on each other, but you can sum, for instance, the total momentum, the total self-propulsion, and this is actually the self-propulsion of the cluster. And for an active particle, if you are pushing in this, if you are pushing in some region, it's very convenient to move all together in the same direction. And this is also a proof of the fact that being out of equilibrium, you are creating a spontaneous current that keeps circulating in the system without having to inject it from outside. So this wanted to be an overview. Yes, please. Yeah, nice question. With anti-alignment interactions, it depends on how you initialize. Also, it depends a lot on how you initialize your system. For instance, I don't know of works in anti-alignment interactions in active Brownian particles, because I think that people that tried didn't see any proper structure. Okay. Of course, if you put your particles on a lattice, it's a different story, because then you are fixing the interaction, and the point is the arrangement of the neighbors, as it was mentioned in Irene's Giardina's talk on Friday. So, before doing a break, I would like to give some outlook on what is going on now on active matter. And I think some of the interesting directions that one can take, and that we will talk about at least for a couple, are on one hand the self-propelled vertex models, which is a way to represent the dynamics of epithelial tissues, not only considering the energy minimization that you have when you build a vertex model, which is a way to represent a dense system where you have no space, where you have no available room, but you tessellate the space to create, to mimic the behavior of an epithelial tissues. But on top of that, it has been seen that you can actually add self-propulsion to this, and this makes the model out of equilibrium. And with this, will be what Silke will be speaking about in the next time. Another thing that I find interesting, and it's also my research work in the last years, is pulsating active matter, which is what happens when you don't actually you don't inject energy, you don't define an activity as a self-propulsion, but is when you define activity as the capability of a particle to change its shape, and we'll speak about that if we have time. I would like to mention that also there is a nice recent ongoing work on how activity changes phase transition, especially on melting. And this has been also recently observed both in papers by the group of Chate and others, and in the papers of the group on Maggi and others. And this will be also part of the, I guess, of the topics of Claudio Maggi's talk on Friday. And another very stimulating topic, I think, is the topic of non-reciprocal interactions, which is another way of making things active when you break the third Newton's law and you say that a particle and its neighbor are not experiencing the same force with a minus sign. And this is, and what I want to say so far is that all this is not what we learned in physics from undergraduate courses. It's all broken, and this is why we cannot actually rely. And I'm also quite cold on also equilibrium mappings of active matter, because I always have the feeling that there is something missing. Then there is also the debate about the relevance of term in the thermodynamic limit. But I think that most interesting part is that being freed from the equilibrium constraints. This is what can give you lead you to many patterns and collective behavior, which is what I was showing you before. And at this moment, I think that we are in between finding very interesting phenomenon like propagation of waves in epithelial tissues or predator-prey behavior in non-reciprocal interactions, and a zoo where actually finding what is the right model, what is the most interesting model is sometimes the hardest question. And with this, I'd like to stop this part.